Okay, chapter 6 in this book starts with counting techniques, and we're not talking about just like counting up how many things you see. We're talking about figuring out how many ways something could happen or how many possible scenarios there are. And for computer science, that can be important to understand, what techniques you might have. If it's a giant problem, you can't just run through all the possibilities and look for the best result. Um, and for math, obviously, there's lots of reasons with probability to know the size of the problem. So, in this first video, we're going to look at a couple of the simple rules for counting techniques. A couple of the examples we see here, these are sort of practical examples. How many four-digit PIN numbers are possible? PIN number is like something you would use for your ATM card. It turns out there's not really a lot of combinations, which might be a little bit troubling, except there is an extra security measure built in that if you make an attempt at the correct PIN number 3 times and you're incorrect, it'll just keep the PIN number. So understanding the sort of how many options there are, how many different possible PIN numbers there are can affect how you deal with the security of it. Same thing with passwords, 8-character password. We could see, how many possible passwords there would be, and then sort of debate, or think about what you could do to make it more secure, all sorts of things like that. So we're just going to look at a couple basic rules. The rules that will get covered in this section are the multiplication rule and the addition rule. The addition rule is a little bit more complicated than just straight addition. It involves sometimes some subtraction. We'll get into that in a little bit. Before we get into these examples, which are maybe practical and more interesting, I wanted to sort of start with something that we know is a little bit easier to manage, and we're going to take a look at some coin tosses. Okay, so we're going to start off looking at a sort of simple example where we have 3 coin tosses. And we're going to talk about a coin that can come up either heads or tails on the first toss. So if we flipped one coin, that one coin would have 2 possible results. And this visual we're going to use here is a tree diagram just to kind of introduce the rule. Um, it's not practical to draw these once they get big. In fact, sometimes even drawing just one this size, you can have things sort of overlapping and it can get complicated, right? But the first coin has 2 choices. Now, depending on the choice or the result of the first coin, right, you also have 2 possible results for the second coin, right, heads or tails. Same thing, if you had a tails first, the second coin could be heads or tails. So this is called a tree diagram because each of these paths is sort of considered what we call branching, right? And you sort of have this multiplied effect here. Right? You had 2 choices for the first coin. Each of those 2 choices had another 2 choices for the second coin. Okay? And then when we get into the third coin, right, we're going to have the same scenario. Tails, and you can see how these get sort of hard to draw. You have to anticipate how much space you're going to need. Right? The idea of doing 8-character passwords where you can use uppercase, lowercase, all sorts of things like that just doesn't make a lot of practical sense. So we're going to look at this one example. You could see here that if you follow all the top branches, you would get heads, heads, heads. Right? That's going this way. Right? And then if we went this way, we would get heads, heads, tails. Okay? Right? The next one would be heads, tails, heads, and so on, right? All the way down the bottom path, which would be tails, tails, tails. And if you count these up, 1, 2, 3, 4, 5, 6, 7, 8, right? There are 8 possible ways that you could flip 3 coins. Right? Now, if we try to analyze, what would happen in this tree diagram, the other way to think about it is we basically had three independent decisions, right? In this case, coin tosses. We had the first coin, we had the second coin, and we had this third coin. We had two choices for the first, two choices for the second, two choices for the third, and as we said before, they had this multiplied effect. Okay? Now this is basically the same as if we were going back to truth tables and logic, right? Where we had true, 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 false, right? We said that if we had three propositions, that each one of them could be true or false. That's like having three coins that could be heads or tails. We had 8 possible truth assignments. And if we had 4, it would be 16, and so on. So you get this multiplied effect, and we call this basically the multiplication rule. We can use this anytime we have independent decisions here, right? The next choice can be determined based on the first choice or independent of the first choice. But if we have basically an experiment or some sort of result that can be broken into stages, you could just figure out how many options you have at each stage and multiply them together. Because for every choice you make at the first stage, you have a certain number of choices at the next and then the next. Okay? So we're going to go back and sort of look at this 4-digit PIN number, right? When you're trying to either make up a PIN number or guess a PIN number, right, you have a bunch of choices to make. In fact, you have 4 choices to make. So we can think about, the first digit, the second digit, the third digit, the fourth digit. Okay? Now, how many possible PIN numbers are there? Well, any of these digits can be 0 through 9, which is actually 10, right? Because 1 through 9 is 9, throw in the 0, you get 10 choices. So you have 10 choices for the first digit. Okay? 0 up a little bit. Okay. Now the second digit, right? We always have to think about this as we start looking at more complicated examples. We have to wonder, is there any reason that the digit you chose for the first one can't be used again? Right? Well, with PIN numbers, you could have a PIN number that's 1111 if you wanted. Maybe it wouldn't seem so random, but you certainly could have it, right? But if you were pulling 10 names out of a hat, right, then you couldn't pull the same name twice, right? So you always have to sort of think about whether or not the result of the first stage of the process has any impact on the second or third or whatever. But in this case, all 10 digits are available in all 4 stages. Now, when you're answering these, obviously a calculator can give you a nice, simple numeric answer. I'm fine if you leave it in sort of unmultiplied out form, like 10 to the 4th, or even 10 times 10 times 10 times 10 shows me the basic principle. I'm going to assume at this point you could put that into a calculator. I'm not too concerned about that stage. What I really want to see is that you can sort of understand that 4-digit PIN number is really 4 separate digit decisions. Each one has a choice of 10. Now, if for some reason you couldn't repeat digits, then you'd have 10 choices for the first, you'd have 9 for the second, 8 for the third, and so on. And we'll come across some examples like that. Here's another example. You had a restaurant, you have a 3-course meal, right? You have 5 appetizers, 7 entrees, 3 desserts. Possible number of 3-course meals. Here you have 3 decisions to make. You have appetizer, entree, and dessert. And you would have 5 choices, and then 7, and then times 3, and multiply that out. Okay, 5 times 7, 35 times 3. That's 105 possible 3-course meals you could order. Okay, and one of the things about this is these things can get very big very quickly. We're going to take a look here at a bit string example. This is a 5. It looks a little bit like an S, but I'll make it look like 5. We're going to talk about a bit string. And just a quick, review. Right, a bit, right, is short for binary digit. The B for binary, and the it from digit. Bit string just means 5 binary digits. So something like 10010. That's 5 digits. 01101. Right? If we were going to be sort of systematic about it, we would be counting from 00000 all the way up to 11111. And the question would be, how many of them are there? Right? Well, we have 5 digits, right? 5 bits. Each one has 2 choices. So we would have 2 for the first, 2 for the second, 2 for the third, 2 for the fourth. These are getting a little messy here. 2 for the fifth, right, which turns out to be 3, 2. Pen was working for a while, and then it got sort of kilter. Now, let's say we knew that this bit string started with 0. Right? Well, normally, or in the last example, we have 5 different digits, right, to choose. But if we know the first one's already a 0, oops, 0 up there. If we know that the first one's a 0, you don't have any choices there. It's just one choice, right? Now the others could be 0, 1, 0, 1, 0, 1, 0, 1. Again, it's a multiplied effect because each choice for 1 has independent choices for the next. This will give us 2 to the 4th or 16. Ending with the 0 is basically the same answer, right? Because instead of having the first one fixed at a 0, the last one would be fixed at a 0, which would just swap the order of these two, would still have 16. Now here's where it gets a little bit interesting. Right? What if we wanted to count the ones that start or end with a 0? Now you might think, well, I'll just take the 16 that start with a 0 plus the 16 that end with a 0 and say there's 32 of them, right? Now, one of the big problems with that is we know there's only 32 overall, right? So there can't be 32 that start or end with a 0. Here's one that doesn't do either, right? So it's got to be a little bit more complicated than that. We do want to think about all the ones that start with the 0. There's 16 of those. And we want to think about all the ones that end with the 0. There's 16 of those. And at some point, on some level, we do want to add them together. And just try to clean that up. The problem is, let's look at a specific string like this one here. Right? This one starts with the 0, right? So it's going to be one of these 16 here. It also ends with a 0, so it's going to be one of these 16 here. You can't count this bit string of 5 twice, right? And if we have the 16 and 16, we're going to be counting it twice. So the key here is when we say or, we want to think about all the ways we can do one part, all the ways we could do the other, and put them together. But we have to be careful that we don't double count. And in this case, we would be double counting all the ones that both start with a 0 and end with a 0. Okay? So if we think about all the ones that start with 0 and end with 0, right? 1 here, all the others are 2. So what we see here is that there are 8 that have been double counted. So if you vary these 3 digits, any variation of those would still give you a string that starts with 0 and ends with a 0, right? These 8 here are the ones that are double counted. So it's not 32, it's 32 minus 8, which in fact is 24. Okay? So the or here, it does mean usually plus, right? But it also means minus. And there's a fancy name for this. This is called the inclusion-exclusion principle. I don't really like to get too bogged down in rules here. I like you to just kind of think about the process and figure it out. Okay? I want to work through just a few more examples here. This first one here, you have 25 juniors, 30 seniors. You want to pick one junior representative and one senior representative. You're only making 2 choices. Right? You have 25 choices for the first, and you have 30 choices for the second. Okay? Now, if we're just going to pick one representative, right, then you would have 55 choices, right, because you could pick anybody. Here's a bit string of length 8, just like the one we did. So if there's no restrictions, you're going to have 2 times 2 times 2 times 2, 8 times. Right? I would write it out as the blanks first and then sort of recognize that. This video is just getting a little long, so I want to kind of work through these a little bit more quickly. The first bit is a 1, right, which means the other 7 can be varied, so you would have 2 to the 7th there. The first bit is a 0 and the last bit is a 1. So the first and last are fixed. That means the other 6 are up for grabs and could be anything. This is going to be another sort of interesting, complicated idea, the idea of at least one that's a zero. Okay? Sometimes it's easier to count the things you don't want rather than count up all the things you do want. If you've ever been in a situation where they ask people to raise their hand and almost everybody raises their hand, it might be easier to count the couple of people who didn't raise their hand rather than the people who did raise their hand. So if we try to think about all the ways there could be at least one bit that's a zero, it gets very complicated very quickly. We could try to find all the bit strings that have 1 0, and then all of them that have 2, and then all of them have 3, and so on. That gets very complicated. But if we try to think about all the ways that there are no zeros, how many of those are there? Right? There's only one. Right? Only bit string that has no zeros is the one that has all zeros. I mean, all ones. Right? So we know in total there are 2 to the 8th bit strings. We know that there's only one of them that doesn't have at least 1 0, which means all the others do. So if we think about it and try to count the opposite effect, right, we can just remove the ones we don't want to count rather than count up all the ones we do want to count. Okay? One more quick set of examples. How many different routes can you plan to visit 5 different cities? Well, here you have 5 cities to visit, right? And you have 5 choices for that first city. Now, this is a case where once you've visited that city, you're not going to visit it again. So you have 4 choices for the second, 3 for the third, 2 for the fourth, and 1 for the last. And again, this is a multiplier. You choose first. You could always choose any of the remaining 4 next. Okay. Here's another OR probability. I sort of circled the word OR, which is something you should sort of be encouraged to do. You have 10 red cars, 15 sports cars, and 5 are both red and sports. So you want to take the 10 red cars and the 15 sports cars together. Right? But it turns out that 5 of them will have been counted twice. We do want to count them once, we don't want to count them twice. So we remove one of those counts, and we're going to end up with 20 distinct cars. Right? How many of bit strings of length 8 would start with a 1 or end with a 0? Well, starting with a 1, that would be 2 to the 7th. Right? Ending with a 0, we know that's going to be 2 to the 7th. Right? Once one digit is fixed, the other ones are all free. Right? But how many of them start with a 1 and end with a 0? Right? How many are left here? There's going to be 6 bits. Right? So 2 to the 6 of them are going to get double counted. Okay? Now, when you're checking your answer, it's probably good to actually get your calculator out and work this out, but I'd be okay leaving your answer like this and just calling it a day. Okay? So right now we're just limited in the amount of techniques we have. We're either going to be multiplying a bunch of answers together or we're going to be adding, possibly subtracting. These are sort of the entry-level cases. They do get more complicated, and we'll add some new techniques, and then we'll have to learn how to